Okay, thank you. So the background of this title page is a survey. I will not tell you which one, or it's not one that I did. It looks like point sources, right? If this was SKA or ngVLA, it would look different. Yeah, we get spatial dynamic range that rivals the abilities of the screen. And that's very important for pretty pictures. It's hugely important for doing consistent science in the continuum, where we rely on such a large wavelength range combined to do our science. What I'll talk about specifically is galactic magnetism from the perspective of the THOR survey, which is an acronym that doesn't seem to have continuum in it. Although, oh my, where's the, I practice this, C-O-N-T-I-U, it's there. It was a bit of an afterthought to do the continuum as well. It's doing the spectral lines in L-band, all sorts, initially in this section of the inner galaxy, and it's recently been extended, or we're processing the data all across the galactic center. Plus or minus a quarter, it looks right through the disk. There's a sister survey that has been great contact in C-band that does the same thing in C-band, basically Glowstar. And I'll show you some results about the combination of these two in the polarization. So galactic magnetism at radio waves, Faraday rotation is an effect, like it's birefringence, difference in propagation of the left and right hand circular polarized waves that is sensitive to the direction of the magnetic field. The net effect is that it twists the plane of polarization along the direction of propagation of the wave, which depends quadratically on the wavelength, and that's how we measure it, right? So we analyze the polarization angle as a function of wavelength squared. Now, if you're not so much in polarization and magnetic fields, one thing that I want you to take away, maybe, is that this formula that I think maybe everyone here in this room has seen is not always true. The issue gets whenever we are looking at a region where different parts of the region experience different amount of Faraday rotation. Okay, and that is both confusing and exciting because it allows us to investigate basically the small scale structures, say the turbulence. So there's a bit of shift of terminology where we call this integral, that is basically the slope of the relation between polarization angle and Laplace squared. We call that the Faraday depth, a little bit in analogy, but it's optical depth, although this can be positive and negative, it can go back and forth. And call the traditional word rotation measure to relate that to the derivative of the polarization angle with respect to Laplace squared. You might think that's the same, but it's not always the same. I'll come back to that. So if you measure the Faraday rotation of extragalactic sources shining through the Milky Way with THOR, this is we have assembled more, but this is what what I have available for you right now. Sorry, I can't use that. You see here rotation measures as a function of galactic longitude. Before we started, the largest rotation measure in this section of the Milky Way galaxy was 800 radians per square meter. Okay, so this shows the value of surveying without bias and being sensitive to parameter space far beyond your expectations. And it went way beyond our expectations. The huge spike that you see here, which we published in this paper 2019, is coincident with the the direction where a line of sight is tangent to the Sagittarius spiral arm. A little bit on the inside, actually. So we have spiral arm traces all the way to or just beyond 50. It's a little bit on the inside of the Sagittarius spiral arm. The Faraday rotation gets this strong. But there's much more in this image. If you look on the inside, lower longitude, you see that the scattering rotation measure is much larger than at higher longitudes. Yeah, there's no coincidence. The error bars, the formal errors, are the size of the symbols here. Okay. So you see that lines of sight through that Sagittarius arm have a much more larger rotation measure scatter than lines of sight that don't intersect that. So somehow that arm does a lot to the Faraday rotation. Imagine that in this part of the inner galaxy, large parts of the Milky Way are thought to cause negative Faraday rotation. But the net Faraday rotation that we detect is positive. It seems to be to a large extent the Sagittarius arm. Now, that region of positive Faraday rotation has been known for a very long time, and you may have heard about magnetic field reversals, etc. But what this shows, this spike associated with the spiral arm shows very much ties that positive Faraday rotation to the arm. There must be positive Faraday rotation outside the arm as well, because we see it at higher longitudes. But this really ties, the magnetic field must be what we call counterclockwise in that arm to get this effect. Now, the scatter here from such a relatively narrow region around the line of sight is also something that requires much more investigation. For example, there's no way, I found no correlation between the rotation measures and, say, distance of the line of sight to the nearest H2 region or something like that. So while the fact that the scatter is large, but the rotation measure remains positive, might suggest this density effect, it may not just be that simple. Imagine that you observe a galaxy outside a local group with a certain beam, say your spatial resolution is smaller, you get all of this inside your beam. And that's Faraday dispersion that I'll talk about next. So if you have a turbulent plasma that creates, has structure on all kinds of scales, inside and maybe as a foreground screen, then you get different amounts of Faraday rotation within your beam. That's hard to avoid. If you have structure across, then you can solve that by getting higher angular resolution. But if it is different regions along the line of sight are integrated with different amount of Faraday rotation, then you cannot. So in a way, we can tell the difference by going to higher resolution, and that, of course, has been tried as well. But if you have the same kind of turbulence farther away, you include larger structures in your beam, and you get basically larger differential Faraday rotation within your beam. Yeah. Now, for this reason, until recently, I would say, common wisdom was that the differential Faraday rotation that we now can measure by observing over a very large wavelength range, like this is a simulation of such a sort, so of course we can choose our wavelength range very large, that it causes depolarization of our radio sources or whatever source we're looking at longer wavelengths. That this depolarization for extragalactic sources was purely due to a plasma near the source for this effect, because the same kind of turbulence would create larger differential Faraday rotation within our beam if it's close to the source than if it's in the Milky Way. True, but it turns out now that there is an effect. So this was first seen. Oh, that's something interesting. Okay. That's interesting. That did not disappear on my, neither a PDF nor a PowerPoint that they had. Okay. Anyway, it was just helpful in relation to this. So we see this is one of our very high signal-to-noise THOR sources. We see this, it behaves a bit like a damped harmonic oscillator where the oscillation wavelength is the rotation measure and the dampening has to do with like this dampening factor, this sigma is the Faraday depth dispersion. Okay, now if we measure that along the plane, then we see it actually increases this Faraday depth dispersion. And there was supposed to be a histogram here, and I could convince you that the Faraday rotation it's about a 99% confidence effect here. We see it a higher dispersion at the lower longitudes. Okay, this had been seen once before by Livingstone et al. 2021, two fields in the one field near the galactic center. Combining with glow stars, so now we include THOR and C-band, we found some sources where this is actually quite strong. Okay. So this is the C-band data. It's a small minority, so I would call this a few percent of the population, but we get sometimes rather strong effects, which is important for the it shows the importance of the shorter wavelengths. Also, I want to briefly, if you can see the data points, this is a model with a constant rotation measure, independent of wavelengths, plotted on data that clearly cannot follow that model. Okay, and we see actual variation of the Faraday rotation, of the rotation measure, of the slope that would create basically intrinsic scatter in measurements of Faraday rotation in short wavelength ranges. I'm running out of time, so I'll be very brief. We're looking at rotation measures, at supernova remnants. We can get quite a bit of detail. This square shows very large variations of polarized intensity and rotation measure. Focusing on this is just this one point where we have very strong signal, where we see this dampening as well in the supernova remnants. And last thing I wanted to show, it's a different one, but there's a paper coming up where of a supernova remnant where we measure that depolarization. So this is Faraday dispersion across the supernova remnant. And in this part, we have no detections, but fortuitously, we got an unpublished Effelsberg map, 6 centimeters. It has a higher beam, so it should measure less polarization because of the higher beam, but actually it measures strong polarization here, where we have upper limits at the 1% level. And that goes to a similar kind of bias against some of the strongest depolarization that you have, even if you have 1 to 2 gigahertz data. Okay, so thank you very much. I'll just put up my conclusions and hope there's time for questions still.
Time for questions? Are there any questions online?
I have 100 questions, but I would have to answer them.
Oh, there's one.
Thanks for the talk. As you go to higher angular resolution, are you seeing a length scale across? Can you get anything to give you an idea of what might be going on?
No, I've asked Robert Lang about that, who's done this for radio galaxies, but no.
When the VLAS polarization data eventually come in, will that be useful to supplement what you already have here?
I'm looking at VLAS with great anticipation, but also a little trepidation because I have to think about the spatial scales that's sensitive to. Yeah, but indeed, there's a lot of depolarization happening in S-band, And that will be very interesting indeed. Yeah.
There are no other questions. We'll go ahead and thank our speaker.
Thank you.